So we were doing the theoretical analysis of the fire plume, where we made a lot of simplifying assumptions. So first one is we consider a point source from which the hot plume is rising up, and the second assumption was the profiles of velocity and temperature are top hat profiles. Instead of a Gaussian profile, it was taken as a top hat profile with some average u and t values at every z. So it's a function of z at every z. So this is z direction basically. Okay, so this is taken as uniform profile. The second assumption. Third is at every point here, the density change within the plume is considered negligible, so that rho is taken as rho infinity when this term appears basically as a single, like for example independent term. When you say mass flux rho u, we can say rho infinity into u and so on. But when you want to calculate the buoyancy force, then we take the difference of this rho infinity minus rho, where this rho is a function of temperature at the particular result. So this is T at a particular result. So based upon that, which is called Bosnick's approximation, we are dealing the force, buoyancy force as the ambient density minus the local density at a particular height z, which is a function of temperature Tc. But everywhere else, say for example mass flux, momentum flux, etc., rho, if you say rho u, I can say rho infinity u, like that. Okay. So this is the another set of assumption what we make. Then radiation heat loss is neglected. Then there is a entrainment of air from the ambient, which has a velocity of v. Now we are dealing with variables already, which are velocity, temperature, and b, the radius of the plume. So now added to this, we don't want another variable v. So what we say is the v is dependent anyway, the internal velocity is dependent on the plume velocity at a particular height. So we can say v, the internal velocity of the air, is proportional to u, or the proportionality constant taken as alpha. I can say v equal to alpha into u. So these are the assumptions we made, and the conservation equations, actually what we derived for the continuity, we get this. Basically you can see that when the mass flow rate is written as rho density u velocity into pi b square the area. Now this rho, you can say I have put rho infinity, that is rho u is now taken as rho infinity u, and area is pi b square. Similarly here rho, what is actually in the expanded thing, you can say rho u z pi b at a particular z square. So here this is the conservation of mass, which is after simplification written as equation A. Then we went to momentum conservation. The rate of change of momentum, that is mass flow rate into velocity with z. So that is equal to the buoyancy force. So again you can see that viscous force is neglected. So buoyancy force, as I told you, is arising due to the density difference between the ambient and the plume at a particular height into g into area. So rho delta g into delta rho will be the buoyancy force basically. Okay. So based upon that, I get this equation for the momentum conservation, where this term is delta rho by rho infinity. So this will discuss this. Then we will now consider the energy flow, where there is a fire and a plume goes over this plume. Now this fire generates some heat q dot, some amount of q is lost through radiation, some amount of q is given back to the fuel for heating it, and this plume carries some amount of heat by convection. So that QC can be taken as 60 to 80% of the heat generated Q in the flame. So that Q dot C is called convective heat flow, which is mass flow rate of the plume, that is rho U pi b square into the specific heat of the hot gases Cp into delta T, which is nothing but T at any Z minus T infinity. So now, in order to write the density difference in terms of temperature difference, the ideal gas law is used. Rho T remains constant because rho goes as 1 by T, and so rho T remains constant. So rho T at the plume or in the plume region will be equal to rho infinity T infinity. So using that, we have simplified. Another assumption made is T tending to T infinity, this goes to 1, this tends to 1. So now I can say delta rho by rho infinity equal to delta T by T infinity. So using this, the conservation of momentum is written like this: d by dz of b square u square equal to q dot c convective heat flow rate g divided by rho infinity pi u cp T infinity. So now there are two equations. Now the two unknowns are b and u. Okay, to solve this, we assume that along the z direction, so please understand that there is no variation of u or t with respect to the lateral direction, only along the height z direction only these vary. So I can say similarly the jet radius or the plume radius also varies in the z direction. So I can say this variation is not linear. So I can say b varies as some constant time z power m, some power law profile. Similarly for u, C2 into z power n. So when substitute these two in the equation A, which is the mass conservation, I get equation C. We have seen this. Now in the equation C, the power of z in both the sides should be same. So when you equate it, I will get the value one equation in terms of m and n. Now do this for equation B, which is the momentum conservation. Apply these two there, and I get equation D. Here also I can equate the powers of z in the left and right hand side, so that I will get one more equation involving m and n. When you solve these two equations and simultaneously, you get the value of m and n. So in this case, I am getting m as 1, n as minus 1 by 3. Now substituting this back into equation C and D, I get equations E and F, where you can see that C1 and C2 are involved in these two equations. When we solve these two, I get the values of C1 and C2. C1 is 6 by 5 times alpha, C2 will be 25 by 48 alpha square, Q dot C G by pi rho infinity Cp T infinity whole power 1 by 3. Now C1 is known, C2 is known, M is known, N is known. So as per the definition, B equal to C1 Z power M, M is 1. So 6 by 5 alpha Z, U equal to C2 into Z power N, N equal to minus 1 by 3. So you can see that the plume radius increases linearly with Z, U decreases with Z. Okay, this is what we have seen. Now we continue here. What is the conservation of buoyancy? We have seen the buoyancy term is G B square rho infinity minus rho divided by rho infinity. Now this is the convection term for the buoyancy. There is no diffusion, etc. So this is the conservation equation for the buoyancy. D by dz of B square, U comes here because of the convective term. So B square Ug delta rho by rho infinity will be equal to 0. So that means this term in the bracket B square Ug delta rho by rho infinity will be a constant called B, the buoyancy. Now you know that the convective energy flow rate Q dot C equal to m dot P Cp delta T, which is pi b square rho u Cp into delta T. From this equation, I know that one more thing what I know is delta rho by rho infinity equal to delta T by T infinity. I keep both delta rho and delta T as positive. That means here delta rho will be equal to rho infinity minus rho, because rho infinity is greater than rho, but delta T will be equal to T minus T infinity. Do you understand? So that is what is the expression here is. So now from this I try to write the ratio of T minus T infinity by T infinity in terms of this, from this equation. So substitute this equation and get this equation. So now I get the value of B as Q dot C G pi rho infinity C infinity into T infinity. Do you understand? So from this is the equation. Either I write in terms of rho or I write the buoyancy in terms of T infinity as a delta T by T infinity. Now I can find delta rho by rho infinity, which is equal to delta T by T infinity as this. So I get a, so substitute these values and simplify, okay, because you know value of B, which is nothing but 6 by 5 alpha Z. Similarly, U is C2 into Z power minus 1 by 3. Substituting this, and I get the value of delta rho by rho or delta T by T infinity as 0.863 B. B is this value, please understand, B is this value, power 2 by 3, alpha power 4 by 3. Okay, now B is also a constant, alpha is also a constant, but again empirical constant, and Z power minus 5 by 3. That means the density difference, normalized density difference delta rho by rho or delta T by T infinity will vary as Z power 5 by 3. So that is what the, so this is called Plume solution. So now we have found the radius, how the radius varies with Z, that is linearly it increases. So U decreases, U basically decreases with Z because it is having a Z power minus 1 by 3 term here, and similarly delta T by T infinity decreases when Z increases. So now mass flow rate also can be found, because you know B, you know U, rho can be taken as rho infinity. Substitute this and get the expression for mass flow. So from this simplified analysis, I can get approximate Plume solutions. Because we have made several assumptions, that means the solution what we get will be approximate, will be indicative solutions only. And also we have considered point source. So now see that, but the trends are got, B flume radius increases linearly, that is observed. Similarly, the velocity decreases as Z power minus 1 by 3. Temperature difference decreases as Z power minus 5 by 3. Then M, mass flow rate of the plume, what happens? Mass flow rate of the plume increases with Z because of the entrainment. Some mass is coming from the point source. As the hot gas propagates, entrainment from the ambient occurs. The air from the ambient entrains into this plume. So the mass flow rate increases with Z. But please see that this all depends on the convective heat flow, the strength of the fire. See, convective heat flow is proportional to, say, I can say 0.6 to 0.8 times Q dot, which is the heat release rate. So all this, for example, if you take the temperature difference, this is delta rho by rho or delta T by T, you will see that B term comes here. The B term is nothing but it has Q dot C term there. So strength of the plume indicates the magnitude of this differences, and the Z power minus 5 by 3 indicates how it decreases with the height. In this case, the mass flow rate increases with the Z. Okay, now please understand that these are all solutions which are got by a simple analysis, but they are approximate solutions. Relative comparison can be made between different fires, how the plume strength will vary, how the U will be varying with Z, how T will vary with Z, etc. Similarly, how the mass flow rate will occur and so on, increase with Z and all. But relative comparison is possible, but for a real fire, we cannot say this is absolute value of the mass flow rate of the plume because of the fact that several assumptions have been made. That means we now can make lot of improvements in this solution. So, say for example, a crude assumption was the rho here is taken as rho infinity. Then we can keep as rho itself and do it, correct? But in the case when you do that, then rho variation with Z also will be affecting this. That means when you try to find T, etc., it will become some more complicated. But it is possible to do that. So, as far as the improvements are concerned, we can get rid of some assumptions, like we are now saying that the plume is generated from a virtual origin, correct? So, there is a point source. From this the plume is generated like this. Now, when fire is involved, a fuel surface is involved. That means there is a finite area for the surface. So, it may come somewhere here. You understand? So, this is the fuel surface. The fuel surface has a finite area. Point source does not have any area. So, now what I can do is I can introduce one more variable, which is the distance between the, this is virtual origin or point source, correct. What is the distance between the fuel surface to the point source or virtual origin? That is called Z0. So, what I say is the fuel bed, which has a finite area, is located at a height of Z0 from the virtual origin. So, that I can introduce, first point. So, the point source approximation can be rectified by considering virtual origin, which is at a distance of Z0 from the actual fuel surface that has a finite area. Second one is, in the profiles we have considered top hat profiles. So, why we did it? Basically because if you see the real plume, the velocity profile it is considered, the velocity profile will be something like this. So, Gaussian type profile we will have for velocity, correct. Now, what we have considered is, so this is clearly maximum velocity occurs at the center, this is center line. So, maximum velocity u0 will be maximum and it goes to 0 value at the edge of the plume, this is plume edge. So, the maximum velocity occurs here and goes to 0, correct. Now, even you assume a uniform velocity, so u here, this is the sort of average velocity. That means I conserve the mass. Whatever be the velocity profile in the Gaussian form, if I want to find the mass flow rate, I will say rho into u, integrate that to get this mass flow rate per unit area here. Similarly, this average velocity what I have considered u, that into density will give the same mass flux. So, only thing is I will not have any radial component. So, for example, this is z direction and it is radial direction. Let us assume a circular area for the bed. Now, if I try to consider the Gaussian, then I have to consider the radial component also. But if I consider uniform, then the problem will be reduced to one dimensional for us. So, that is why we went for uniform profile. But now, we can replace the top hat temperature profile or top hat velocity profile to more realistic Gaussian profile like this. That is second thing what we can do. Okay. So, first thing is avoid the point source, but yet consider some virtual origin which is at a distance of z0 below the actual fuel surface. Second one is top hat profile can be replaced by Gaussian profile. Gaussian profile, you know some mathematical relations for this, some curve fit and do this. Third is the flame radius. A flame radius is defined as the radial location where the temperature has reduced to half of the center line value at a given height. So, again I consider a plume at a given height. I draw the temperature profile, the plume basically. So, here the temperature reaches the ambient temperature like this. Similarly, in this direction also. Okay, now this is T naught, which is the maximum temperature. So, the flame radius or the plume radius can be considered as some distance here, okay, or which will at this point the temperature will be T naught by 2. That is, the center line temperature has reduced to half of the value at a given radius. That is taken as flame radius or plume radius. Now, either I can take temperature profile or I can also take a velocity profile also. That means I have velocity which is maximum at center and it drops to 0. At a particular radius, okay, it will drop to u0 by 2. So, that also I can take as plume radius. That is, the plume radius can be taken based upon the temperature profile where the center line temperature drops to half of its value at a particular radius, or it can be taken as the radius at which the axial velocity, central velocity decays to half of the value. Now, when I incorporate this, I get some solutions, improved plume solutions. First of all, the radius of the plume. As I told you, there are two ways to consider that. When I say BT, it is based upon temperature profile, where the center line temperature has decayed to half of the value. So, these are correlations. Basically, these expressions are obtained with the support of experimental measurements. So, I can say BT is 0.12 into T naught, that is the center line temperature at a given Z. Please understand, this is a function of Z. So, T naught is the T naught at a center line temperature at a given Z divided by ambient temperature power 0.5. So, as I told you, some experimental support is there for this correlation into Z minus Z naught, where Z naught is the origin, virtual origin. Okay. So, now you can see, but even though you do this, you can easily see that B is a BT or B, where is as a function of Z linear function, which is what we got in the simplified solution also, correct. But this is more accurate because now we have assumed a Gaussian profile, we have assumed that the point source is not there, there is a finite source, but we consider virtual origin. The next is, if T naught is the center line temperature at a given Z, okay. Now, delta T is nothing but T at any Z minus T infinity. Okay, now delta T naught will be equal to T naught at any Z minus T infinity. When I say delta T, it always represents the difference of the temperature, given temperature with respect to the ambient temperature. Now, a correlation. Now, a correlation for delta T naught. So, we already, if we go back, I have a correlation for delta rho by rho, which is equal to delta T by T infinity. Okay. So already I got a correlation from simplified analysis which says temperature difference proportional to z power minus 5 by 3, correct. Now here also when I improve solution I get z power minus 5 by 3, that trend, but it is more improved solution because we have considered now the variation of temperature along the radius also. Delta T naught, so T infinity is going there, so delta T naught equal to minus, sorry, plus 9.1 T infinity q dot c square by g Cp square rho infinity square power 1 by 3. So these are all constants into z power minus 5 by 3. So again the variation trend along z is same, minus 5 by 3 is the value there, but again you can see the virtual origin is put in here. Okay. So the improved solution also preserves the trend because we are just trying to improve solution from that. But what we are trying to do here is we have some experimental measurements to support the correlations. What you the expression what you some constant we are putting here like this here. These constants are got from some experimental measurements also. With the support of that we are building these correlations. So improved plume solutions. So that is what we want. The strength of the plume, again you can see that the temperature difference is higher when QC will be higher. The mass flow rate of the energy flow rate of the plume, convective energy flow rate is higher, then the delta T naught at every Z will be higher. So that is another important thing. Again you can see that the QC can be written in terms of basically the temperature at a particular Z minus T infinity. Now U naught is center line velocity. Okay, at any z, u naught at any z depends on z power minus 1 by 3. That is, u naught varies with z as a function of z power minus 1 by 3. Okay, now these solutions, what we have got, they are called strong plume solutions. That means the plume is strong enough, first of all, that is, the fire is very strong, and we are not considering a very weak plume. That is, the plume, if the convective strength arises from the heat release rate. These solutions are going to be valid only when, because they have been supported by experiments where the fire is strong enough. Okay, so the expressions given here will be valid for strong plumes. If the plume is weaker, then there will be some discrepancies with the results what we obtain using these experiments when you compare with the experiments. Now one more thing is, we are considering a pure plume region. That means Z is much higher than, that is at least 2 times higher than HF. Z is higher than HF. Within the flame zone, none of this will be valid. Because there will be a strong temperature gradient as opposed to the weak TC. The temperature gradient will be like this in the flame zone. Okay, but in the plume zone it is like this. It's a weaker. The temperature difference from the center line and the flame zone, this is TF, this is the center line temperature T naught. So now the maximum temperature difference will be between TF and T infinity. Here it is T naught and T infinity. You can see that the T naught will be much lesser than TF. So the expressions, these expressions are valid only in the plume regime. Obviously, because we are considering only plume regime here. Now, to impart some finite area, we are considering some virtual origin. This is estimated when the centerline temperature as a function of z is known accurately. We can do this. Okay. So when you go back to the relationship what we have derived for the centerline temperature, we see the dependency on temperature difference is basically dependent with z as z power minus 5 by 3. That means we can say the z can be a function of delta T naught to the power minus 3 by 5. So using that I can get the virtual origin. So once you accurately predict the temperature profile at every height or the centerline temperature itself at every height, then by using this expression here, I can predict the virtual origin. So that is the thing. So that means I can also form a correlation for the virtual origin, correct? Okay. So I got the simplified plume solution, from which I got improved plume solution, which are going to be valid for strong plume relations or strong plume cases, and which are valid for the plume regime. And now the improved solutions involve an estimate of Z naught, correct? That is got when you accurately measure the temperature of central line, and we can get the value of Z naught by understanding how delta T naught power minus 3 by 5 varies. So a correlation for the virtual origin was proposed as 0.083 q dot power 2 by 5 minus 1.02 into D. Similar to flame height correlation, this correlation also is there, where D is the fire diameter and q dot is the heat is in kilowatts. So several expressions are available. These are only some examples. Several expressions are available in the literature for plume solutions.